Hi students, welcome to another video on Bode plots. So in this video we'll see how do we plot Bode plot on a semi-log sheet. So as you know, okay, this is a semi-log sheet. On the x-axis I have a logarithmic scale. So this is actually for the frequency. So I'm having the starting frequency as 0.1. Since it is logarithmically changing, so this is 0.1 means then this is 10 times of that, which is 1. Now it is 10, this is 100, 1000, 10,000. So this is omega in radian per second. On y-axis it is the gain, which is in dBs. So now this is in dBs. So this is in dB. So I have taken this as the 0 dB line. This is 20 dB, this is 40 dB, and below 0 dB I have minus 20 dB, minus 40, minus 60, it goes like that. So every unit is now 20 dB is the dimension. So now let us draw the plot for this transfer function, which we already discussed in the previous video. So we have actually drawn this plot so on a white sheet. Now let us draw the same thing on a semi-log sheet with the data what I have, So now, so let us start with this transfer function. So we should know what is magnitude at the origin for this particular transfer function. So magnitude at the origin is 20 dB with omega is 0.1 at the origin. You can see this is 0.1 radian per second. So the magnitude is now 20 dB is the magnitude. You can see this is 20 dB. So this is my point. So this will be 20 dB till the first cutoff frequency. The first cutoff frequency comes at 10 radian per second, which is there here as 10 radian. So what I'll do here is, so I'm just doing the jigger. So now this will be 20 dB line till 10 radian per second. So I will just draw this line till this 10 radian per second, which is now this is, can you see now, this is 20 dB line till a frequency of 10 radian per second, because the cutoff frequency is there at 10. So after 10 radian per second there is a slope of 20 dB per decade. So we were discussing how do we plot 20 dB. So it was asked to come down 20 dB and go 1 decade. I will exactly do the same thing now. So now this is 20 dB. I'll come down by 20 dB down. So this is 20 down means this is now 10 dB, 0 dB. So you are actually came down by 20 dB down, go 1 decade. 1 decade means this is 10, decade of 10 is 100. So that is 10 times of this. So now this is, so now if I join this line, that is this and this, so then it will be a slope of 20 dB per decade. So I will join from here to here. So now this is a line with a slope of minus 20 dB per decade. How did I come? So from this point, which is 10 radian per second, I came down by 20 dB and went by 1 decade. So this is my reference point. I joined this to this. So this is 20 per decade. So that's what we wrote it here. Then so we are now at 100 radian per second. Now we are there at 100 radian per second. As per the table, if you can see here, at 100 radian per second the resultant slope changes to minus 40 dB. So now from here I'll come down by 40 dB down. So I'll come down by, because each unit is 20 dB. So from here I'll come down by 20 plus another 20. So it is 40 dB down here, and I'll go 1 decade here. So this is 1 decade. So you can see now this is 40 dB per decade. Now these two are the points which I should join, so that will be a slope of 40 dB per decade. See, now I'll join these two points. Now this is, now I can continue this till the end because there are no more slope changes. I just joined this dot to this dot, which is now 40 dB per decade. So what is the slope of this? The slope of this is minus 40 dB per decade. So this is my minus 20 dB per decade, this is minus 40 dB per decade. So this can continue till the end. This can continue till the end because there is no change in the slope. There is no change in the slope. This is the magnitude plot of this particular example, which is 10 by 1 plus 0.1 s and 0.01 s. What is that we are trying to understand is, so corresponding to 10 we have a 20 dB magnitude till a cutoff frequency of 10, which corresponds to this. So after 10 it will have a slope of minus 20 dB per decade because there is a first order pole at 10 radian per second. There is one more pole at 100. So this has already started contributing minus 20. The contribution of this also starts at 100 radian per second. So overall contribution of slope is minus 40. So that's why slope changes to minus 40 after 100 radian per second. So as we did in the previous problems, no need to do this individual for 20 dB. This is 0 dB and then 20 here, 0 dB and 20 here, and then the resultant one. You can straight away plot the resultant plot if you have the information about magnitude at the origin and the slope table. So while choosing the magnitude on the y-axis, you have to be careful. You cannot choose 0 dB here. You cannot choose 0 dB here because I know that the slope is always coming down. So there is no point in selecting 0 dB here and then you don't have enough space to come down here. So always take a point which is there closer to the upper half of your Simulog sheet, so that slopes, when the slopes are usually coming down, so it's better to take the 0 dB as towards the upper end as possible. So that's why I just taken this as 0 dB 20 40. I cannot take the topmost as 0 dB because I need to go 20 dB above. So that's why we have chosen somewhere here so that it is effectively visible. So this is how we can plot the magnitude plot of a Bode plot in case of a transfer function which is lambda. Next we'll see how do we plot this particular transfer function. Now this is a transfer function which is, so now it is GFS into HFS, which is now 10 divided by S into 1 plus 0.1 S and 1 plus 0.02 S. Of course, for this also, so let me start writing the frequency 0.1. This is 1, this is 10, this is 100, this is 1000, and this is 10,000. This is omega. The unit is radian per second. This is the magnitude. This is magnitude in dBs. Let me take, because I know that the magnitude of this goes up to, from this table, the magnitude will go to 40 dB. So let us take the topmost as 40. So let us take each unit as 20. So this is now 20. So this is now 0. This is minus 20, minus 40, minus 60, minus 80. This is so on. So this is magnitude in dBs. Now let us start looking from this. So what does this say? Magnitude at the origin, that is ORG. Omega ORG is the origin magnitude, which is origin frequency is 0.1 radian per second. So this is 0.1. At 0.1, what is the magnitude? It is 40 dB. So let us put a point 40 dB here. See now, it is 40 dB. In this problem, you initially have a slope starting from the origin itself. So from the beginning itself, it is not a 0 dB slope line. It's not a slope of 0. It has got a slope of minus 20 dB per decade. So from the beginning itself, because you have a slope of minus 20 dB from the beginning itself. Maybe you can see in the previous case, the cutoff frequency was there at 10. So till 10 it was 0 dB. So after 10 this is minus 20. So how you should read is, after 10 the slope is minus 20. After, this is your resultant. After 100 it is minus 40 dB. So now what do you have here? So you have this, there is no cutoff frequency. When there is no cutoff frequency, resultant slope from the initial itself is minus 20. So how do we start now? I know that this is my starting point for a omega of 0.1. So I have to start with a slope of minus 20 dB per decade. That's what it says. So now come down by 20 dB, go by 1 decade. So this is 20 dB down, 1 decade. 1 decade means from 0.1 go to 1. So this is the line which will go till the first cutoff frequency. Where is the first cutoff frequency? First cutoff frequency is at 10. So what I'll do, I will join these two lines and extend this till 10 radian per second, because 10 radian per second is here. So this is my 10 radian per second. So what I'll do, let me join this and this. Maybe you can also simultaneously do it. So now I'm joining this to this, and this will go up to 10 radian per second. See, this has gone up to 10 radian per second with the same slope, because slope is not changing. So at 10 onwards it is minus 40 dB. So till 10 it is minus 20 dB per decade. This is the slope. So after 10 what is the slope? This is after 10 the slope is minus 40. So this is 10, afterwards it is 40 dB down means, so you come down by 2 dimensions, go by 1 decade. So this is 40 dB per decade. Now you should join this point to this point, but you should stop it at next cutoff frequency. Next cutoff frequency is not at 100, it is at 50. So what I'll do is, I will identify, you can see 100 is this, 50 is somewhere here. So you can see this is 1 means 10, 20, 30, 40, 50. So if you can see here, so there are numbers written. I hope you can able to, if I zoom it out, can I? It's difficult to zoom it. I don't know. So this is what is written here. Maybe you can see in your graph sheet. So this is 1, this is 2, 3, 4, 5. So this is 5. So I will try to join this and this using dotted line. I'll use a dotted line from here to here, but I'll make it solid till 5. So where is 5? So 5 is here. So from here to here I'll make it solid. See now? So this is my solid one. Dotted one continues to here. So dotted I wrote it, this is a slope of minus 40 dB per decade till 50 only. At 50 it stops. Okay, this is 50. This is 50 here. So this is now slope of minus 40 dB per decade. You may ask a question, why did you go up to 100? Because this is 40 dB per decade. I cannot stop it at 50. So I cannot stop it at 50 because the slope is minus 40 dB per decade. I came down by 40 dB. I have to take the reference as 10 times of this, which is 100. Then this is your reference point, but drawing this line should stop at 50, because at 50 I have a different slope. So now what is the slope at 50? It's actually 60 dB per decade. Now I have to be careful. From this point I have to come 60 dB down. So this is now 10, 20, 30, 40, 50, 60, because each subdivision is 10, 10. Now this is 10, 20, 30, 40, 50, 60. Now it is 60 dB down, go by 1 decade. So 1 decade means you are there at 50, you have to go to 500. 500 is again 5 here, 5 into, so I think it is this one. So you can see it's on the same horizontal line. So this vertical is 5. So 5 into 100 is 500. So now I have to join this line. So now from this 50 to this 500. From this 50 to 500. See, I'm joining this. So this is having a slope of minus 60 dB per decade. 60 dB per decade. And of course I have a 0 dB line here. So this is the 0 dB line. Maybe I can just darken that. This is 0 dB line. this is 0 degree line. Correct? This is how we will plot a graph with a pole at the origin, which will result in a slope of minus 20 dB from the beginning. Let us find the difference here. You can see the slope was not there initially because the first cutoff frequency is at 10. So at 10 the slope changes. Next is at 100. So at 100 again the slope changes. In this case, there is a pole at the origin itself, so that's why the slope initially starts with minus 20, and then at 100 it adds another 20, so that minus 20 plus minus 20 is minus 40. At 50 it again adds, so at 50 the slope changes to, you already had minus 40, you are adding another minus 20, so it will become minus 60 dB per decade for this particular problem. So I want all of you to do this problem once on the semi-log sheet, and then make sure that you get a hold on how do we plot the graph, especially coming down by 40 dB 1 decade and stopping at some point, which is, suppose if the cutoff frequency comes prior to this, suppose the frequency was at 200, then you would have extended this up to 200. So 200, how do you make out 200? So it's unfortunately I cannot, this is not visible. Can I? No, this is actually 2, 3, 4, 5, 6, 7, 8, 9. So when you actually see in your graph sheet, it's visible. So these are given as 1 to 9. Depending on your value, you need to multiply 2 into 100 is 200, 300, 400, and this will be 2000, 3000, 4000. This will be 0.2, 0.3, 0.4, so like that. Okay, thank you. So we will see, of course we still not yet seen we have not yet plotted the phase plot, and we not found the stability of the system, so that we'll see it in the next videos. Thank you.